All right, so here we're going to do a section on proving identities, trigonometric identities. I'm going to start with a warm-up. Consider x squared minus 4 over 10 onto x minus 1 equals negative 1 over 2x minus 2 plus a half, okay? We don't know if this is a true mathematical statement or a false one, but we're going to try and figure out if it's true or false. We're not going to bother doing any algebra, though. Instead, we're going to do that by evaluating the left-hand side and the right-hand side and seeing if they're equal. So, warm up, step 1. Evaluate the left-hand side and the right-hand side with x equals 2. See what you get. And then the follow-up question is, does this prove that this equation is true? Pause the video here and go ahead and do that. All right, now is this what you got? 0 equals 0? If so, does it prove that the equation is true? And the answer is no, it doesn't prove it. It just shows that the equation holds for this value of x. But it doesn't prove that it's true for all x. For this to equal this means that it's true for all x. And we don't know that that's true yet. Okay, here comes warm-up number 2. So now I want you to do the same thing, but with x equals 3. It's the exact same equation. Evaluate the left-hand side, the right-hand side for x equals 3, and then answer the question, does this prove that the equation is true? Pause the video, go ahead and do it. All right, did you get the left-hand side equal to the right-hand side again? A quarter and a quarter? If so, well, very good, but here's the question once again, does it prove that the relationship there is actually true? And again, of course, the answer is no, it doesn't prove it. It might give us more confidence that perhaps it's true because we've seen that it's true for two different values, but it doesn't prove that it's true because, again, for it to be true means that it works for every single x. Okay, here comes warm-up number 3. So now I want you to evaluate the left-hand side and right-hand side of this exact same equation for x equals 0 and tell me, does it prove that the statement is true or not true? What do you get? Pause the video, give it a shot. Is this what you got? 2/5 and 1? Now, of course, this time it's false. Does that prove that these are not equal? Can we assert now that the left-hand side is not equal to the right-hand side? This time we can. We can say the left-hand side does not equal the right-hand side because equality means that it works for all x's, and here we found an x where it doesn't work. So you only need one example where it doesn't work to prove that the equation is not true. Whereas you can go through as many possible values that do work, and it won't prove that it's true. Okay? So that's the upshot of what I've got you to do here, is to get at that concept that you could go and show that the left-hand side and right-hand side are equal as many times as you want, 10, 100, 1,000, a million. It still won't prove that they're true because it has to be true for infinitely many values, for all of them. Whereas if you find a single time that it's not true, that does prove that it's false. Okay, so now, given that, let's take this example here. Let's move into trigonometry. So this question says, verify that 1 minus sine x squared equals sine x times cos x times cotangent x by using a special angle. Okay, you're going to see questions like this where they're asking you to verify that something is true. Now, you've got to be careful to keep in mind that it doesn't mean that you're proving it's true. You're just showing that it might be true. And the more values you plug in that show the left-hand side equals the right-hand side, the more confidence you have that it might actually be true, but it's not a proof. A proof requires something else, and I'm going to be showing you how to do a proof later on this section. but verifying with a special angle is not a proof. On the other hand, if you find an angle that you plug in and it shows that the left-hand side is not the same as the right-hand side, then that proves that the equality does not hold. Okay, just like before with the algebraic example, with the polynomials and rational expressions, I guess they were. Okay, so now I'm going to verify this using a special angle. In this question, it's leaving it open to me which special angle to pick. Anything I want. So I don't know, I'm kind of partial for pi over 6. That's equal to 30 degrees. I like it. So I'm going to use pi over 6. So I have 1 minus sine of pi over 6 squared. I'm going to just write it this way to emphasize that this notation means that it's sine of x all squared. And I'm going to put sine of pi over 6, cosine of pi over 6, cotangent of pi over 6. Now, I haven't actually memorized what that is, so I'm going to rewrite that as cosine of pi over 6 over sine of pi over 6, because that I know I can do. Okay, so what do I have on the left? I have 1 minus 1/2 squared. So that's going to be 1 minus 1/4, which is 3/4. Okay, so let's see if the right-hand side is 3/4. If it is, then perhaps this statement is true. If it's not 3/4, and I didn't make a mistake anywhere, then it's definitely false. Sine of pi over 6 is 1/2. Cosine of pi over 6 is root 3 over 2. Cosine is root 3 over 2 over sine is 1/2. Okay, and let's see here. So this is a fraction divided by a fraction. So I will, I'll just well, actually, I can do the multiplication here. So I'm going to get root 3 over 4 times root 3 over 2 times 2 over 1. And then the 2's cancel. I'm going to have root 3 times root 3. That's 3 over 4. Indeed, they match. Now, does it prove it? Does it prove that this is true for all x? Of course it does not. But it gives me some confidence that maybe there's something here. Maybe it actually is true. Okay, so now the next example is going to be prove it. And I'll show you how exactly we go about proving trigonometric identities. This is called an identity because the left-hand side is identical to the right, and we're about to prove it. So here's the question here. Prove that 1 minus sine x squared equals sine x times cos x times cotangent x. Now, first of all, a rule. You may only work on one side of the equation for your final answer. With trigonometric identity proofs, you are not allowed to go from side to side. And I'll talk more about that as time goes on, but I'm going to put that rule there for you right now. And then secondly, a tip. So you may recall from another video, tip number 1, it is often helpful to convert to sine of x and cosine of x. That was tip 1. Here comes tip 2. Tip 2 is that it's often helpful to work on the messier side when you're doing an identity. So if I look at these two sides, I have 1 minus sine x squared and sine x, cos x, cotangent x. I would say the right-hand side is messier. So I'm going to work on that side and try to make it look like the left-hand side. So here we go. I'm going to take my cotangent and I'm going to express that in terms of sine and cosine. That's actually tip number 1. So this would be cosine of x over sine of x. And now I notice here that I can cancel out the signs because one's in a numerator, one's in a denominator. Just like very quickly here, if I had 5 times 4 times 3/5, I could cancel the 5's. Okay, so I'm left then on the right-hand side with cosine x squared. That's good. That's pretty simple. Can I somehow make that look like 1 minus sine x squared? Well, I can, because we have the Pythagorean identity. Sine x squared plus cos x squared equals 1. So if I subtract sine x squared over, I get that cos x squared equals 1 minus sine x squared. So in fact, I can go ahead and on my very next step, I say 1 minus sine x squared. And if I wanted to be really nice to the marker, I could even put here Pythagorean identity. That would be an extra step that goes above and beyond to make it crystal clear to my marker why I think I can go from here to there. Now that my right-hand side equals my left-hand side, I am finished. Okay, so I'll put a small square. So now this brings us to tip 3. If you want to work on both sides separately in scrap work, that's okay. And I'm going to talk more about what I mean by separately in a minute. That's okay. You can work on both sides separately in your scrap work, but for a formal proof, you must rearrange your work so it's all on one side. Okay, so I'm going to do this exact same question again, but I'm going to do it in kind of a scrap work kind of a way, where I'm working on both sides separately, and then I'm going to use that scrap work to make a formal proof. So here we go. I'm going to still use tip number 2, which says work on the messier side, but I'm going to pretend this time that I get stuck. So I'm working here, I'm going to work the messier side. I'm going to use tip number 1, where I rewrite cotangent in terms of sine and cosine. So I have sine of x, cosine of x, cosine of x over sine of x. And I see that these, whoops, I see that these cancel there. So I have cosine of x squared. And then I'm kind of stumped. I can't figure out what to do, okay? Let's suppose. So then I'm like, okay, well, now let me go over to the left-hand side and work on this side and see if I can somehow do something here that matches what I have on the right. Okay, this is what I'm doing in my scrap work. What I cannot do ever in formal or in scrap with a trigonometric identity proof is I cannot say subtract 1 on the left and the right. That would be working on both sides at the same time. Not separately anymore, but simultaneously. You can never ever work on both sides simultaneously. I can't subtract 1 on both sides. I can't multiply both sides by something. I can't divide both sides by something. That's just simply not allowed. Often we say, imagine that you have a wall here in the middle. You can't go across. These are two separate problems. And basically, we're looking at it as though we have a simplification problem and a simplification problem separately. Okay, so I can work on them separately in my scrap paper. Suppose I'm stumped right to there, and I come over here on the left and I say 1 minus sine x squared, 1 minus sine x squared. Gosh, that seems familiar. And maybe even let's pretend that I forget that that's cosine x squared, but I do remember why, I don't know. I remember that sine x squared plus cos x squared is 1, and so sine x squared must be 1 minus cos x squared, okay? Let's suppose that that's what I remember. And so I'm going to replace sine x squared with 1 minus cos x squared, like that, okay? That's my next step. And then I'm like, I'm getting close. I know I'm going to distribute this negative sign. So I get 1 minus 1 plus cos x squared. And I'm like, okay, eureka, I've got it. Because 1 minus 1 is 0. So this equals cos x squared. And now my two sides are equal. Okay? So now if I do that, then I've done what I say is I've broken the proof. I've solved the problem. I've broken the problem. I know what to do now because working each side separately, I was able to get to the same final step. If you work both sides separately and you get to the same expression on both sides, then what you need to do to finish it off is you take either side and you go backwards in putting your steps. So let's suppose I'm going to keep this right-hand side. This is what my proof is going to look like. Then my next line here is the line before the line that equals it. So this one right here, I copy that out right underneath. 1 minus 1 plus cos x squared. It actually looks as though I'm very cleverly adding 1 and subtracting 1 for some reason, which is fine. In fact, sometimes when you get proofs, you've seen them in the past, where somebody's cleverly adding and subtracting something. It might be because they actually proved it or solved it some other way, but the way they present it looks like this. Then I take the very next line above it and I put that next, okay? So now I have 1 minus bracket 1 minus cosine of x squared. And then I take the next one above it, in this case now this is going to be the final one, and I put it there. 1 minus sine of x squared. That's what I wanted to prove. I have done it. So I can put my little square. Now if I do this, for my formal proof, this is all just scrap work now. I don't want to hand this in, but I've got my proof on the left. So all I have to do now is just copy out exactly what I did on the left. So my original question would say, prove 1 minus sine x squared equals sine x cos x cotangent x. And I'm just going to step by step copy everything that I wrote on the right-hand side right here. Cos x over sine x. The sine x's go. I'm left with cos x squared. Then what did I put next? Well, then I put this magical plus 1 minus 1 business. So I just copy that out. Plus 1 minus 1 plus cos x squared. What did I do next after that? Well, then I put brackets there. 1 minus bracket 1 minus cos x squared. What did I do next? Well, then I was able to turn this into sine x squared, 1 minus sine x squared, and I'm done. Okay, so now here I have a correct formal proof based on this scrap work proof. So I'm going to add in a rule here just to be super explicit. Even for scrap work, you may not ever, under any circumstances, work on both sides simultaneously. Okay? You can work on this side by itself and work on this side by itself in scrap paper, and then use that technique I just showed you to make a good proper proof. But you may not, under any circumstances, do the same thing to both sides of the equation. That will not lead to a correct proof. Okay, so now I'm going to just walk you through several proofs. I'll do a few examples, and then I'll let you work on some proofs of your own. So this one here, I want to prove that tangent of x equals 1 minus cosine of 2x over sine of 2x. I'm going to use tip number 2. I'm going to start with the messier side. Now, if I can work just on this right-hand side and get all the way down to tangent of x, then great, I've got my proof. If, however, I get stuck and I want to start messing around over here, that could be fine for scrap work, and then I'll use the technique that I showed you before to make a formal proof. So, okay, right-hand side. This sine of 2x, I'm going to rewrite as 2 sine of x cosine of x. That's pretty much a no-brainer because over here, my argument is x. Over here, my arguments are 2x. I have to make the arguments the same. So this one pretty much has to turn into 2 sine x cos x. That's the only double angle identity that we have for sine, and that's the only way to make it match the x that we have on the left-hand side. Okay, so that's fine. Now, in the numerator, I have a few choices, right? I have 1 minus 2 sine x squared. I have 2 cos x squared minus 1. I have cos x squared minus sine x squared. Now, which one should I pick? I'm going to pick, and I could be wrong, I might have to go back to this step and try it again, but I'm going to pick the one that has a 1 in it, so that I get 1 minus 1 and the 1's go away. That will make things simpler, right? So I'm going to pick 1 minus 2 sine x squared, just like that. Okay, now I can simplify my numerator, so the 1's go away, which is what I wanted. Minus a negative is the same as plus a positive, so that's nice too. So this is making me pretty happy, because I see that in my numerator and denominator, all the terms are multiplied, so I can cancel out the 2's, divide top and bottom by 2. That's good. I can see that I can also cancel the signs, so this is looking good to me. And I'm left with sine of x over cosine of x, which is, of course, tangent of x. So I've got it. I've proven it here. Okay? Now, there's no one right way to do these proofs. They take trial and error. They take intuition. They take, logic. And they take practice, quite frankly. So the more you play around with trigonometric identities, the easier these proofs will become over time. Also, if you memorize the identities, it will make them stand out to you more easily when you see them, right? Like if my question started with this, then in that case, it would never be clear to me that this is the same thing as sine of 2x. And if I needed that in my identity, I'd be pretty much stuck. I'd be racking my brain, how can I deal with this thing? Whereas if I have memorized my identities, this just pops out at me as obviously sine of 2x. Now, in this particular case, we actually started with sine of 2x and picked this out. That's a little bit easier. But either way, you have to kind of see what these pieces are and kind of know what potentially they could be made equivalent to in order to do the proof. So memorizing the identities is very helpful. Here's another proof. This one's pretty similar to the last one. It would be a nice place for you to try your first trigonometric identity proof. If you want to pause the video and try this one, I'd recommend it. See if you can tackle this one here. All right, so I'll do it here. I have that, I have 2x and 2x on the left and a single x on the right. So clearly I'm going to be using double angle identities. Moreover, sine of 2x only has a single possible identity. It's 2 sine x cos x. And I'm working the left-hand side here because it's messier. And that's one of the tips. Working the messier side is usually easier. Now, I'm going to rewrite cosine of 2x as something. And ideally, it's going to be the something that subtracts off 1. Because if I can subtract off 1, then that's going to cancel with this one here. So I'm going to use the 2 cosine x squared minus 1 form of the identity for cosine 2x. Okay, so then I get 2 sine x cos x over, this becomes 2 cos x squared. I can cancel, and cancel. I get sine of x over cos of x, and of course, that is tangent of x, which equals my right-hand side. Actually, it used to be fashionable that at the end of these proofs you would say equals right-hand side and maybe put a square then. Doesn't really matter. I don't care about that. All right. Let's do another one. Let's take an example here like this. So this is a great example where it is oh so tempting to do the wrong thing. When you see this, or at least when I see this, I am just so tempted to so-called cross multiply and go sine x times sine x is sine x squared. 1 minus cosine times 1 plus cosine, like this. That's going to be 1 minus cosine plus cosine. Those cancel, minus cos x squared. And indeed, that does equal sine x squared. So I feel like I've done it. But you know what? This is complete garbage. This is not a proof. You cannot work on both sides simultaneously. Okay? So this is unfortunately just a waste of ink. What I must do is work on only one side. Or at the very least, I could work on both sides separately and then make my formal proof. So, okay, which side should I pick? Not really sure. There's not really a messier side. It's not really so clear to me. Now, wow, I know what to do here. One thing I might be tempted to do is write this as 1 over sine x minus cotangent x, and then see if I can somehow get this into a 1 over sine x minus cotangent x. Not so simple, not bad. Here's what I'm going to do. This 1 plus cos x is a bit of a nuisance. So, by the way, is this 1 minus cos x. It's a bit of a nuisance. So what I'm going to choose to do is multiply the numerator and denominator on the right-hand side. I'll work the right-hand side by the conjugate of the denominator. Watch how this works. It's a bit of a trick. So if I multiply numerator and denominator by the same thing, then that's fine. I'm not changing the amount. And what do I get? Well, let's just write the numerator like this. I don't really know where this is going to go, so I'll just write it out like that. The denominator, though, I'm going to multiply out. I'm going to FOIL. 1 times 1 is 1, plus cosine x minus cosine x, so those cancel out, and then minus cosine x squared. Okay, now see, this is good because cosine x squared is useful in terms of the Pythagorean identity. I still haven't maybe necessarily seen what the whole proof is going to look like, but it's starting to feel okay. Especially, by the way, I have this here. This matches this. So that's good. That could be actually another reason why it might feel reasonable to multiply numerator and denominator by the conjugate, because the conjugate here actually is part of what we want to end up with. So I'm looking at my denominator now. I'm going to use the Pythagorean identity. I'm going to rewrite cosine of x squared. And I'm going to rewrite it as what? Well, I have the sine x squared plus cos x squared equals 1. So cos x squared is 1 minus sine x squared. So I have 1 minus bracket 1 minus sine x squared. That's a correct application of the Pythagorean identity. So that's fine. And now I have a bit of simplification that I can do here. I like that. 1 minus 1, that's 0, minus negative. So I now have sine x over times 1 minus cosine of x in the numerator over sine x squared. Now I'm feeling really good. Can you see how this is going to end up? I can divide the numerator and denominator both by a sine x, and I'm left with 1 minus cosine of x over sine of x. And that's what I wanted. There it is. That's the left-hand side. Done. My proof is complete. All right, here's one more. So I look at this one and I say, boy, okay, I've got lots going on. First of all, I have cotangent, cosecant, cosine, and sine. So that's a bother. I may want to put it into sines and cosines. I have x's as arguments and 2x's as arguments. So that's a bit of an issue. The right-hand side is messier, and it will get even messier when I deal with this sine 2x and turn it into 2 sine x cos x. So I'll probably work the right-hand side. I might even end up working both sides and then doing a formal proof. Let's see here. So on the right-hand side, I definitely want to write 2 sine x cos x right there. And generally speaking, I will probably want to factor this sine of x out. Why? Well, generally speaking, when we can factor something, that's a good thing. Normally, if we can factor in the denominator, we hope that we'll get the same factor in the numerator and that they'll cancel out. So I'm keeping an eye open for the potential to factor both, factor out a sine of x. Numerator, I've got to do something with this cos 2x. And of course, I have 3 options. So let me mull them over here for a second. I could have 2 cosine x squared minus 1. I could have 1 minus 2 sine x squared. And I could have cos x squared minus sine x squared. Let me think through each one. What would happen? Well, with the first one, I would have a 1 hanging out. I would have only cosines. That could be okay. I don't know. Sometimes we're just going by gut intuition. I mean, this looks like it would make a quadratic, a 2 cos x squared, and minus 1 cos x, a minus 1. Maybe that could be factored. So that's tempting. If I look at this one, I still have the 1, and then I have a minus 2 sine x squared. I'm not as excited about that because I'm mixing sines and cosines there, and there's nothing that can really be factored. Now, I could apply the Pythagorean identity to it afterwards. That's an option, but so far I'm less enthusiastic about this one. And let's look at this last one here. If I put that, I can't factor anything because I still have a mixture of cosines and sines. So I'm not so enthusiastic about that either. So I'm most enthusiastic, what I think is most promising is the first one because I see it can be factored. So I'll try it and I'll see. And if it doesn't work, hey, nothing's in stone. I can go back and try something else. Okay? So that's what I'm going to try here first. Let's rearrange it so I can factor. And while I'm at it, I'll factor the sine x in the denominator. So I'm left with 2 cosine of x plus 1. See, I'm kind of hoping that this is going to be one of the factors when I factor the numerator. Let's see here. This is 2 cosine of x squared minus cosine of x minus 1. This is like 2u squared minus u minus 1. What does that factor into? It's a 2u and a u, a 1 and a 1. I guess that's the minus and that's the plus. Let's double check. 2u times u is 2u squared. minus 2u plus 1u, that's a minus 1u, and then minus 1. So this is correct. So now let's do the factoring. This is 2u is my dummy variable for cos of x plus 1, and cos of x minus 1. Let's see here. 2 cosine of x plus 1. I'm going to double check that I did that right. 2 cos x times cos x, that's 2 cos x squared. Good. Minus 2 cos x plus 1 cos x, that's minus 1 cos x. Good. And minus 1. Good. Okay. So I factored it correctly. And yes, these cancel. That is great news. Okay. This makes me confident. I have a cosine of x minus 1 over sine of x. Now, where am I headed again? That's right. It's a difference of two things. So I guess what I'll do is I will write this minus this. I'll split it up. I'm going to go one step slower just to show you how this is allowed. This is like the fraction cos x over sine x minus 1 over sine x. Actually, I guess that's not one extra step. That's just literally what it is. Okay, because this would be the same as cos x minus 1 over the common denominator of sine x. So that's correct. This is cotangent x. This is what? Well, it's cosecant x. How close are we? Or do we have it? We got it. That's it. Okay, so I didn't even need to work on both sides separately here. I was actually able to pull it off just working the one side. Done. That proof is finished. Or what I remember now, actually, what used to be in vogue is you'd put equals left-hand side here, and then you'd put your little square. Doesn't matter, though. You can stop it right there, too. That's fine. No problem at all. Okay, so this is good. I think that you've got enough of a sense here that you can try a bunch of your own. Now, this really is a matter of practice. The more you practice, the easier it will become. It takes practice. No two ways about it. And it's on a very special page. It's on page 100 pi, approximately. Right? 3.14? Yeah. Okay. So these are the questions to work on. Good luck. Dig in and enjoy. It's fun. I like proofs. I hope that you enjoy them too.